This is a short tutorial on how to use the Thirsty Duck TDP series design tool. The engineers at Thirsty Duck have developed a very useful design tool for generating rating curves for the TDP series floating outlet and skimmer. The tool can be accessed from the Thirsty Duck website and allows the design engineer to quickly create the unique rating curve associated with each of the Thirsty Duck's available orifice diameters throughout their corresponding ranges of operating head. The tool also includes a series of calculators which are very useful when designing stormwater detention and flow equalization systems. The first worksheet in the design tool is for data entry. Note that data is only entered in cells which are shaded in yellow. Data which appears in cyan-shaded cells has been pre-selected by Thirsty Duck and should not be changed without first consulting a Thirsty Duck engineer. Values which appear in black are values which have been calculated based upon user input. Most user input cells include tooltips. The tooltip will appear when the user hovers the mouse over the cell. Let's review the basic input in the data entry worksheet. The first cell is for the project name. The project name will appear at the top of all subsequent worksheets and printed reports related to the TDP series rating curve. The second cell is the vertical datum, to which all subsequent elevation data is referenced. Typical input may be MSL, mean sea level, NGVD 29, National Geodetic Vertical Datum of 1929, or NAVD 88, North American Vertical Datum of 1988. The third cell is the TDP series model number. When the cell is selected, a button appears immediately to the right of the cell. The button activates a drop-down menu which allows the user to select the appropriate model number. The fourth input is the nominal orifice diameter, for which a rating curve is desired. Enter this value in inches in the English version of the design tool and millimeters in the metric version of the tool. The next series of inputs are the system design elevations. The maximum storage elevation is the maximum possible elevation at which water may be contained in the system. For an open pond, this would be the elevation of the top of bank. For an underground storage vault, it would be the elevation of the vault's ceiling. The diagrams on the screen illustrate the maximum storage elevation for both an open pond and an underground vault. The minimum discharge elevation is the lowest level at which water may be discharged from the system. The diagrams on the screen illustrate the minimum discharge elevation when Thirsty Duck controls the system water level, and when Thirsty Duck does not control the system water level. The design peak stage is the maximum elevation available for storage. If no freeboard is required in the system, the input will be the same as the maximum storage elevation. When freeboard is required, the input will be the maximum storage elevation minus the required freeboard. The diagram on the screen illustrates the difference between the maximum storage elevation and design peak stage. The design tailwater elevation is the elevation of the hydraulic grade line, or HGL, at Thirsty Duck's location. This value may need to be calculated separately by the design engineer, based upon the sum of all inlet, outlet, friction and elevation losses downstream of the Thirsty Duck. The elevation of the HGL should be computed at Thirsty Duck's design flow rate. So long as the HGL is below the elevation of Thirsty Duck's flow restrictor, any value below that elevation is an acceptable input. The design engineer is cautioned this value does not represent the elevation of the water's surface at the final project outfall. The diagram on the screen illustrates the correct location of the HGL for the tailwater input. The design operating head is the depth of water over Thirsty Duck's flow restrictor module, which will yield the desired flow rate. The user will typically vary this input value until the value of the desired flow rate, shown in the cell immediately below, has been achieved. The goal seek function in Excel is very useful for quickly finding the required design operating head. Thirsty Duck recommends rounding the operating head to the nearest 1/4 inch in the English version of the design tool and 5 mm in the metric version. The next series of inputs, installation case data, relates to control of the system water level. If Thirsty Duck's flow restrictor controls the system water level, it is a Case A installation. If the system water level is controlled by a traditional weir or orifice, it is a Case B installation. When the installation case cell is selected, a drop-down menu is activated and lists the 2 installation cases. If Case B is selected in the following cell, input the distance Thirsty Duck's flow restrictor will be installed below the elevation of the water level control device. Note: the value recommended for maximum hydraulic advantage is calculated in the Case B installation worksheet immediately following this worksheet. The diagrams on the screen illustrate Case A and B installations. For more information on Case A and B installations, please see our tutorial on the hydraulic principles behind the TDP series floating outlet and skimmer. The final data entry cell is the rating curve computation increment. Enter a value appropriate for the accuracy of the analysis you are completing. Note: if using the Western Washington hydrology model, enter a value which is 1/100th of the distance between Thirsty Duck's flow restrictor and the maximum storage elevation. The next worksheet in the TDP series design tool is titled Case B Installation. The Case B Installation worksheet is a stage versus discharge calculator for system water level control devices used in Case B installations. Calculators are provided for vertically oriented rectangular weirs and slots, vertically oriented circular orifices, horizontally oriented circular orifices, and horizontally oriented weirs. The calculator will determine the distance Thirsty Duck's flow restrictor should be located below the water level control device for optimum hydraulic advantage. To use the calculator, first select the type of control device from the drop-down menu, which will appear when the device type cell is selected. Then enter the relevant dimensions and coefficient of discharge for the selected device type. The rating curve generation worksheet calculates the stage versus discharge relationship based on the inputs on the Data Entry tab. The stage column indicates the water surface elevation. The buoyant static column indicates whether Thirsty Duck is resting on its nest or whether Thirsty Duck is floating. The free or submerged discharge column indicates whether Thirsty Duck's flow restrictor is producing a free discharge or is functioning as a submerged orifice. The TDP flow restrictor elevation column indicates the elevation of Thirsty Duck's flow restrictor. The values in this column account for initial elevation below the control device in a Case B installation, changes in water surface elevation, or stage, and the slight increase in the depth of flotation resulting from forces developed in the bellows as Thirsty Duck rises. The control device inflow column indicates the theoretical flow rate over the water level control device, based on water surface elevation, for Case B installations. The TDP flow restrictor discharge column indicates the theoretical discharge through Thirsty Duck's flow restrictor, based on the water surface elevation, and the elevation of the flow restrictor shown in the TDP flow restrictor elevation column. The total discharge column indicates the system discharge rate. The value in this column is the lesser of the values displayed in the control device inflow and TDP flow restrictor discharge columns. The rating curve plot worksheet contains a graph of the stage versus discharge relationship. The Export tab is a summary table of the Thirsty Duck rating curve. This table is provided for easily copying and pasting the data into third-party hydrologic and hydraulic analysis packages, which require a stage versus discharge format. The stage versus area worksheet is a calculator for developing the stage or elevation versus area relationship for rectangular-shaped underground vaults, tanks, or open ponds. The stage versus area relationship developed in this worksheet also appears on the SSD Table Worksheet. The Stage versus Discharge worksheet calculates the stage versus discharge relationship for a multiple orifice outlet riser, which includes the TDP series floating outlet and skimmer, defined by the data entered in the data entry worksheet. The stage versus discharge relationship developed in this worksheet also appears on the SSD Table Worksheet. The SSD Table Worksheet is a summary table of the stage, area, and discharge relationships developed on the previous two worksheets. This summary table is very convenient for copying and pasting the data into third-party hydrologic and hydraulic analysis packages, which require a stage storage discharge format. The Orifice Diameter Selection worksheet contains a chart which illustrates the range of flow rates which can be achieved with each of Thirsty Duck's available orifice diameters. The green bars are for model TDP 184, while the blue bars are for model TDP 248. Now that we've reviewed each worksheet in the TDP series design tool, let's create a rating curve for the following example problem. Thirsty Duck will be installed in a wet extended detention pond with a minimum discharge elevation of 94.00 feet NAVD88. The allowable discharge rate is 1.2 CFS. The top of bank elevation is 98.00 feet, and 1 foot of freeboard is required by the local regulatory agency. Since this is an extended detention system, the Thirsty Duck will be installed behind a 4-foot-long weir, having its crest elevation coincident with the top of the required extended detention volume. The coefficient of discharge for the weir is presumed to be 3.2. The outlet pipe is significantly large enough to allow open channel flow conditions at the design discharge. The HGL will be well below Thirsty Duck's flow restrictor. Start by opening the TDP series design tool and click on the tab to open the data entry worksheet. Enter the project name. For this example, we will input Rating Curve Example. Next, input the elevation datum. For this example, elevations are referenced to the North American Vertical Datum of 1988, NAVD88. Open the Orifice Diameter Selection worksheet. Use the chart to find the orifice diameter, which produces the allowable discharge rate of 1.2 CFS. The chart indicates model TDP 248 with a 7-inch diameter orifice should be used. Reopen the data entry worksheet and enter the model number TDP 248, and then enter the nominal orifice diameter 7 inches. Enter the maximum storage elevation 98.00 feet, then enter the minimum discharge elevation 94.00 feet. Since 1 foot of freeboard is required by the local regulatory agency, enter 97.00 feet in the design peak stage cell, and then enter the design tailwater elevation. For this example, the HGL is expected to be well below Thirsty Duck's flow restrictor, therefore we will enter a value of 0. Using the goal seek function in Excel, determine the design operating head, which will yield the allowable flow rate of 1.2 CFS. Remember to round the operating head to the nearest 1/4 inch. For this example, 9 inches will produce a flow rate of 1.2 CFS. Next, set the installation case to case B. Open the case B installation worksheet and select Horizontal Weir for the control device type, and then enter 4 feet for the weir length and 3.2 for the weir coefficient. The worksheet indicates Thirsty Duck's flow restrictor should be located at least 0.50 feet below the crest of the weir to achieve optimum hydraulic performance. Reopen the data entry worksheet and enter 0.50 feet in the distance below control device cell. Last, enter a rating curve computation increment, which is suitable for the level of analysis you are performing. For this example, we will retain the default value of 0.05 feet. Open the Rating Curve Plot worksheet and you can view a chart of the Thirsty Duck rating curve produced for this example. The numerical data for the rating curve may be viewed in the Rating Curve Generation worksheet or the Export worksheet, as discussed earlier in this tutorial. Thank you for watching this short tutorial on using the Thirsty Duck TDP series design tool. If you have any questions or comments regarding this tutorial, please feel free to contact us through our website at www.thirsty-duck.com. We are always happy to review or assist with modelling at no charge.